All right, thank you for that introduction, and thank you to the organizers for organizing this symposium. Today I'm going to be telling you about some work we've been doing with nickel-substituted rubidox invariants as model hydrogenases. So I know I don't need to tell this audience too much about nickel iron hydrogenase, but just briefly, nickel iron hydrogenase is a large heterobimetallic enzyme with both nickel and iron in the active site, where nickel is the redox active metal that can oxidize hydrogen to protons and electrons, and it can also do the reverse reaction, converting protons into hydrogen gas. So it does this with very high catalytic turnover. It operates essentially at the thermodynamic potential, and it utilizes the inexpensive metals nickel and iron. However, there are a few downsides to its large-scale use. For one, it's large and can be somewhat fragile. Sometimes it's challenging to heterologously express, and some variants are oxygen sensitive. So what we can do, building off work in the 80s by Moore and coworkers, is we can take rubidoxin, which is a small electron transfer protein that natively binds iron, and substitute out that iron for nickel. Once we've made this substitution, we've mimicked the primary coordination sphere of the nickel iron hydrogenase, where the nickel is coordinated by 4 cysteine residues. So some advantages of this system are that it's very small, around 5 kilodaltons, but it's still a very well-folded protein. It's easy to heterologously express in E. coli. It's oxygen tolerant and very bench stable, and it's stable at a large pH and temperature range, making variable temperature and variable pH studies very easy to conduct. So we know that we have a structural model of nickel iron hydrogenase. Next, we wanted to check to see if we also have a functional model. So by using a technique that I know is very familiar in the hydrogenase community, protein film electrochemistry, we can place our iron rubidoxin on an electrode surface and see a reversible 1-electron couple at about 10 millivolts versus NHE. When we then do the substitution for nickel, we see a catalytic current, which we attribute to hydrogen evolution. So not only can we observe hydrogen evolution, but we can also quantify it with what's known as quantitative protein film electrochemistry. So by using a 50-50 mixture of nickel-2 rubidoxin and iron-2 rubidoxin, because the charge is the same and the size is the same, when we place them on an electrode surface, the coverage is the same. So by using the reversible peak from the iron, we can also know the coverage of the nickel. And by looking at the current 100 millivolts past the onset of catalysis and knowing the coverage of the nickel, we can then obtain a turnover frequency. So there's 2 different ways that we can really attach our protein to the electrode surface. The first is through simple electrostatics, where at lower pH values, our protein is more positively charged, and we can attach it to the negatively charged surface of the pyrolytic graphite electrode. The second is through peptide bond coupling chemistry, where we can covalently attach our protein to the electrode surface through the native lysine residues present. So both of these methods work great. However, covalent attachment affords some additional stability. So moving forward in the presentation, I've mostly used the covalent method attachment. So next we wanted to determine the mechanism of hydrogen evolution by the system. So using protein film electrochemistry, we looked at the onset potential versus the pH, and we saw a slope of around 59 millivolts per pH unit. So this is indicative that protonation is coupled to reduction. Next, we looked at turnover frequency versus pH, and we saw only a weak dependence. So in the pH values ranging from 3 to 6, we only saw a little bit of loss of activity. So this indicates that the rate determining step does not rely on proton transfer from water. We saw a small but a normal kinetic isotope effect, which implicates that proton transfer is involved in the rate determining step. And then doing variable temperature studies, we see a negative entropy of activation, which indicates an ordered transition state. So with this experimental evidence in hand, we then turn to electrochemical simulations to help determine the mechanism. So by matching the Schutz to the voltammograms and ensuring that the simulated onset potentials and turnover frequencies match with the experimental results, we're able to determine that we likely have a CE-CEC mechanism for hydrogen evolution. So stepping through this mechanism, we have a nickel-2 resting state. And then we believe we have a proton and an electron come in, forming a nickel-1 intermediate with a protonated coordinating cysteine residue. We believe our rate determining step is intermolecular proton transfer to form this nickel-3 hydride. We have another proton and electron come in, and then hydrogen gas is evolved. So you can see I put this side by side with the nickel iron hydrogenase mechanism, and that they are highly similar. So we believe that we also have a mechanistic model for hydrogenase. So with the structural, functional, mechanistic model in hand, where do we fall short? Nickel iron hydrogenase can evolve gas in the order of hundreds per second. Our turnover frequency is a bit lower with about 31 per second, give or take a few. And while nickel iron hydrogenase operates at the thermodynamic potential, we have a larger overpotential of about 560 millivolts. So there is still a lot of room for improvement between our system and that of the nickel iron hydrogenase. One benefit of our system, though, is that we can easily do mutations to the amino acid residues and still retain fold. So that is exactly what a previous student in our lab did, Jeff Slater, and he mutated 3 of the valine residues in the secondary sphere to a variety of other amino acids. And in doing this, he was able to slightly lower the overpotential, such as with the C34E mutant, and he was able to significantly increase the turnover frequency, such as with this C08E mutant. And while I don't have time to get into the whole story here, what he was able to find out is that local flexibility and protein dynamics do play a critical role in modulating catalytic rates. So to explore this idea further, we turn to nature. So it's often seen in enzymes from psychrophiles that they tend to be more active at room temperature compared to their mesophilic or thermophilic counterparts. And this is often attributed to dynamics. So enzymes from psychrophiles need to be active at low temperatures, they can be more dynamic and active as the temperature is raised. Likewise, enzymes from hypothermophiles tend not to be as active at room temperature, but their activity often increases as the temperature is raised. So up until this point, our group has used the rubidoxin from the sulfate-reducing bacteria, desulfo vibrio desulforicans. So in order to find new rubidoxin variants to study, I generated a sequence similarity network here, where each point on the graph represents a rubidoxin sequence, and then they're connected based on if their sequence similarity exceeds a certain threshold. So by using this tool, we were able to find another rubidoxin from a mesophile, 2 from hypothermophilic archaea, and then 1 from a psychrophile. So I'm looking at the sequences of these new variants and then comparing to the logo, which is representative of all rubidoxin sequences, we do see many similarities. Of course, the 4 cysteines that bind to the metal site, as well as some other strictly conserved residues such as a proline here, a lysine. However, there are a lot of differences as well. So we hypothesized that these differences may play secondary sphere effects in modulating catalysis. So because these variants all do natively bind iron, we needed to verify that they bind nickel as well. So this was confirmed through UV-Vis, where we could see the D to D charge transfers and the ligand to metal charge transfers indicate that metal has been bound. So one interesting difference between our variant and a new variant that was studied is ours and most rubidoxins have a CXXC binding site in this first binding spot, whereas this new MJ variant has a CXC binding site with only a bulky methionine present between the 2 cysteines. But we did confirm through UV-Vis that it binds nickel and that structure is not really changed because of this coordination site. So next we wanted to see if they're also active for electrochemical hydrogen evolution like the DD variant is. And we were excited to see that they are all active. Unfortunately, none were really more active than the DD variant, which we previously studied. And we do see a loss in turnover frequency when we go from electrostatic attachment to covalent attachment. But this was previously seen for the DD variant and was attributed to a loss of dynamics when the protein is covalently attached to the electrode surface. Because they are all active for electrochemical hydrogen evolution, we can study the mechanism of these as well. So once again, looking at the onset potential versus pH for the DD variant, and then overlaying the new variants on it, we see a pH-dependent onset potential. Looking at the turnover frequency versus pH once again, we see only a weak dependence. And then looking at the kinetic isotope effect values, they all have normal kinetic isotope effects with values that range from 1.5 for the PF to 1.91 for the MJ. So we do believe that all these variants follow the same mechanism as DD nickel rubidoxin. Next, we turn to electrochemical simulations once again to extract some parameters associated with catalysis. So this work was largely done in help with one of our undergrads, Riley Stein, who helped develop the MATLAB script and then also helped run simulations. So we can see that when we vary the pKa value, we are changing our fit to the normalized current versus pH. When we change our K1 values, we change the fit to the turnover frequency versus pH. And when we change our E0 values, we change the fit to the onset potential. So in doing this, we're able to extract these parameters. In fitting the new variants in this same method, We do see that some variants have a better fit to others, such as this PF variant, which has a very nice fit compared to the DD variant, which I just showed, which not so much. However, we are able to see differences between the K1 value, which is our rate of intramolecular proton transfer, and differences in our pKa values. So the differences in the pKa values may suggest a role in the local protein environment and modulating the basicity of that coordinating cysteine residue. So back to our original question, can we correlate activity to the optimal growth temperature of the parent organism? So to do this, we turn to variable temperature electrochemical studies. So at the lowest temperature studied, we see that the PG variant is the most active from the psychrophile. And at the highest temperature studied, the two rubidoxins from the hypothermophiles are the most active. So this is in line with what you would expect from the parent organism. Then looking at the kinetic parameters, the enthalpy and the entropy of activation, it's often seen in native enzymes from psychrophiles that they have a lower enthalpy of activation compared to their mesophilic or thermophilic counterparts. So this is often attributed to low thermal variation in activity because they already have that more flexible framework. Likewise, they tend to have a larger and more negative entropy of activation due to a large difference between the relatively relaxed ground state and relatively ordered transition state. Whereas in hypothermophiles, they tend to have a more rigid ground state, so there's less of a difference between that transition state. And this is exactly the trend that we see here. So in our sample size of 5, we do think that we can see that variant trends correlate to the optimal growth temperature of the parent organism. Next, we turn to light-driven hydrogen production assays to see if these are also active for solution phase hydrogen production. So we use H2ase as a photosensitizer, ascorbate as a sacrificial electron donor. We injected the airspace of the solution into the GC and monitored hydrogen evolution over time. So looking at just the DD variant versus the H2ase standard, it's not unremarkable, or it's not remarkable. We don't see a large difference in activity between the standard. However, we were very excited to see that these new variants are very active for solution phase hydrogen production with log scale now on the y-axis. In particular, this PG variant is highly active for solution phase hydrogen evolution. So we hypothesize that perhaps this high activity is seen in solution that's not really seen on an electrode because the PG variant is able to be very dynamic in solution. However, activity may be constrained when it's on an electrode surface. Next, we did variable temperature assays with the GC as well. So in raising the temperature from 4 degrees C, which is the solid dots here, to 37 degrees C, which is the open circles, we do see an increase in activity for both the PG and the PF variant. However, the activity increases to a much greater extent for the PF variant, 3.7 times as active compared to the PG variant, which is 1.4 times as active. So this is also in line with the growth temperature of the parent organism. So in conclusion, hopefully today I've convinced you that nickel rubidoxin serves as a structural, functional, and as a mechanistic model of nickel iron hydrogenase. That all the newly characterized variants are active for electrochemical hydrogen evolution. That they're active for light-driven hydrogen evolution as well, with this PG variant being highly active. And that the optimal growth temperature of the parent organism appears to play a role in the activity of the artificial enzyme, giving indication that dynamics do play a large role. So this could be a direction to take for other artificial enzymes as well by using various from psychrophilic organisms, and it's a direction that our lab is going to look into in the future. So with that, I would like to thank my advisor, Dr. Hannah Shafat, the current members of the rubidoxin team, the former members, Regina and Sean, who served as great mentors, Jeff Slater, whose mutant library I showed today, Ohio State, the NSF for supporting this work. Thank you to all the organizers of this wonderful symposium. Thank you all for your attention. And with that, I'm happy to take any questions.